Looks like the chair is missing. I'm just wondering if Animesh is around. Okay, so Leslie will be chairing this session.
So here we go. This is the first spotlight session. Everybody gets 3 minutes. And we start with Somil.
Thank you, Leslie. Hi, I'm Somil, and I'm a PhD student at UC Berkeley working with Professor Claire Tomlin. In this work, we are interested in the problem of autonomous navigation, where the robot needs to reach a desired goal position in an environment where we don't know the obstacles beforehand. But we have a monocular RGB camera mounted on the robot, which it can use for navigation. Now, autonomous navigation is a very well-studied problem in robotics literature. On one hand, we have end-to-end learning paradigms, which have shown some really promising results. But I'm coming from a control theory viewpoint, and that there is a load in these systems that we already know, that we don't need to learn. For example, a dynamics model of the robot. In contrast, there are mapping-based approaches which have been using these models for decades for navigation. But we are asking ourselves, can we combine the advantages of learning-based methods with the model-based approaches? So in this work, we are proposing a novel framework for navigation which combines learning-based perception module with a dynamics model-based planning and control module. The perception module takes as input the current image observation of the robot, along with the speed at which it is moving and the goal position it wants to go to, and outputs the desired next state, a waypoint which is being used by the planning module to plan and control a trajectory for the robot. And we train this perception module entirely in simulation using supervised learning in environments where we know the map beforehand. So we can actually use the optimal control itself to generate the supervision for the waypoint. But we don't use any map information during the test time. And we compare our approach to an end-to-end learning paradigm where instead of outputting the waypoint, we now output directly the control commands, as well as with a mapping-based approach. And what we found is that the proposed framework is way more successful and produce significantly smoother trajectories compared to an end-to-end learning paradigm. And when we looked into the failure cases of end-to-end learning method, it's around narrow corridors or tight corners, which are precisely the navigation tasks which are hard from the planning and control standpoint. Also, I would like to put attention to the performance of the mapping-based approach, which is almost perfect in simulation. Then we took this framework, which was trained entirely in simulation, and deployed it directly on the real hardware testbed without any fine-tuning or data collection in real world. And as you can see, even the robot has never been in any of these two buildings. It can actually navigate smoothly and successfully around the regular office clutter to reach its goal position with only single monocular RGB images. Now, this is where not only the visual feedback, but the dynamics model-based control feedback is super important for this performance. When we compared this approach to a mapping-based approach in hardware, the performance of the mapping-based approach actually deteriorates. That's because of the imperfect depth estimation around thin wires, or power strips on the floor, or thin texture or shiny objects, which ultimately leads to the collision with these objects. But since our framework does not explicitly rely on a map, it does not suffer from those limitations. And for more details, please visit us at our poster. Thank you.